Angelista, and I will be your moderator for today. Just a few reminders that you are in listen-only mode to avoid unnecessary background noise. However, you can type in your questions anytime, and that questions will be answered by our panelists in a Q&A segment. By the way, the recording and certificate will be sent out in 2 days' time for this webinar. And our topic for today is about the advanced transformer testing, which will be presented, fortunately, from Sweden. We have an expert from Sweden, and we are happy to tell you that he's an expert from Sweden. His name, by the way, is Joachim Skolden, the product manager from Megger, Sweden. So without any further delay, let's start the webinar. Joachim?
Yes. Thank you for that, Michael. So I made a webinar earlier this summer. It's summer here in Sweden, so I say summer. I would say in July, which was called Basic. This is more or less part 2, where we continue on where we were the last time when we were left off with part 1. Everything is based on SIGRE Technical Brochure 445, and what I would like to do is just make a very quick recap from what we did last time. So we were discussing standards and how you test the different transformers, how you should test them. And the most common standard is the IEC 60076, where you have -1, -2, and so on, and -18 happens to be the SFRA standard. The problem with these IEC standards is that they define that all the tests shall be done at the manufacturer's work, which means it's not really field applied for the field. And with that, in 2011, SIGRE released a technical brochure, which is called Technical Brochure 445, which is called the Guide for Transformer Maintenance. This guide covers so much more than the electrical tests. It's how you should plan your maintenance, who should do the work, the different components, and so on. But it also relates to the different field tests that you can do. This technical brochure can be downloaded from sigre.org for free, because SIGRE now has released this. So any technical brochure that is older than 2 or 3 years is now free for download. So you can get it at sigre.org. Section 5.1, which is the electrical measurement methods for on-site transformer diagnosis, divides the different electrical tests in 3 parts: the basic electrical, the advanced electricals, and the dissolved gas analysis. Here you see how they are defined in a table and what type of problem you will find. Today, we will focus only on the advanced electrical tests, not all of them, because we don't have the time, and the knowledge base is a little bit spread out over the world for the Megger factories. So all the knowledge is not in our factory where I come from. So anyway, we will focus on the advanced electrical tests. And as this is a small recap, the basic electrical test is the winding ratio or turns ratio, winding resistance, magnetization current or excitation current. It's the same test, different name. Capacitance, dissipation factor, power factor, or tan delta test. Insulation resistance, short circuit impedance or leakage reactance. And then you also have the last one, which is the core ground test. Those were the basic electrical tests that we discussed in part 1. Today, it's the advanced electrical tests. So we will go through the frequency response of stray losses and the frequency response analysis, which is the FRA or the SFRA test. Then you have 3 tests, which is called polarization, depolarization currents, frequency domain spectroscopy, and recovery voltage method. This is PDC, FDS, and RVM, if you look at it in how it's usually said. Those 3 tests are actually very similar. If we say, for instance, turns ratio, the TTR test, it is very unique for finding the turns ratio of the transformer, while the polarization current and the frequency domain spectroscopy, you're actually looking to find the same thing, but it's just 2 different ways of doing it. So these 3 tests, PDC, FDS, and RVM, there is not a big difference, and the actual technique, the only difference I should say is basically how you apply the voltage, but the result of the test is actually the same. So you don't do all of them, you only do one of them. And as I said, I cannot cover all the advanced electrical tests because the partial discharges, I don't have sufficient knowledge, and we have the factory in Aachen that knows very much of all the partial discharges tests. So we can also have a separate seminar for that, or it might already have been taken place. So we will cover the top 5 tests, but I will split them only into 3 because the last 3 is actually the same. So with that, we go to the SIGRE technical brochure for frequency response of stray losses. Now we will be a little bit more theoretical than part 1 because we need to understand the tests a little bit more than for the more simple winding resistance test. So with this, we will find local overheatings due to eddy current losses and stray flux or short circuits between parallel strands. Not all know what a parallel strand is, so I have some pictures coming later on where I will try to explain it in a better way. So even if you don't know it, bear with me, I will try to do this. So the indication for this type of fault is usually a DGA, a high temperature fault. The test method is an AC source with variable frequency in the range of some hertz up to 100 hertz. And you connect it to each phase of the high voltage winding with the secondary side short-circuited. Then you measure the voltage and the current that you send in. This is actually the exact same thing as the short-circuit impedance test. But instead of doing it at the rated frequency, you apply this at a frequency range. And the reference for this is, of course, you compare the 3 phases. And then you look at the delta L and the delta R. It should be less than 2.5% and less than 15%. I will shortly explain the difference with what I mean with the delta L and the delta R. So if we look at the short circuit impedance test, you remember we're looking at the R and the L with the secondary side short circuited. That will give us the equivalent circuit of the voltage, the current, with a resistance and an inductance. So we will actually have only a resistive part and an inductive part. So if we now go back to the interpretation, you see the difference in inductance and the difference in resistance we see here. It is actually how these components change with frequency. So what is the difference between the short circuit impedance and the frequency response of stray losses? It is, of course, the same as the short circuit impedance, but you do a variable frequency. So you do 1 to 500 hertz, but you focus on the resistive part of the measurement. The inductance is part of the measurement. You have a definition of how it should behave and what is the accepted value, but the actual part that you're looking for is the resistive, where the allowed change is 15%. And you try to find short circuit between parallel strands. And then to understand this, we actually need to understand how the strands and how the current and the resistance behave within the transformer, and why we get the eddy current losses and all of these things. So when we look at the R and the X or the L, we can see that the resistance is not constant. We have been taught, and everything tells us that the resistance has no frequency behavior. If we look at a circuit schematic, the resistance is the resistance, and it doesn't matter what frequency you apply. That is a relatively true statement. But when we look at it in a copper conductor, we actually will see a small frequency behavior. So the DC resistance is always slightly smaller than the AC resistance. And the AC resistance will increase when the frequency increases. Why is that? It's because of this one. We will have current flowing in the windings of the transformer, and then the winding have resistance, and the current flow in both windings give rises to the leakage flux. So what happens is, when you have a DC current in a circular conductor like this, the current is evenly distributed throughout the whole area. But when you have an AC current, the skin effect or the eddy current actually makes the current to be thicker, or the current density is thicker along the edges. And in the center, there is actually no current flowing. So the effective resistance of an AC measurement means that the resistance actually becomes higher. And if we look at this a little bit simplified, we can see that all the current is going in the outer surface of the conductor, like this. Here we can also, when we look at it in the simplified view, we can define this skin depth, which is the thickness at which the current density is reduced by 63%. So, due to the skin effect, the effective cross-section of the conductor is reduced when using AC. A smaller cross-section, but the same current, gives an increase of resistance. Hence, the AC resistance is always larger than the DC resistance. If we then look at the frequency and the skin effect, what will happen is when the frequency increases, the skin effect becomes more clear and the skin depth is smaller. Transformer, and we would like to have the transformer to carry a larger current, then we need to increase the conductor size. So then we need to increase. So we go from this size to this size. But in reality, we will have a much larger area in the middle not carrying any current. So actually, it doesn't help us in carrying a larger current. So how do they do when they make the transformer winding? They actually separate these different conductors. So they make smaller effect because you will only have a small part between all these parallel strands. So here is one a parallel strand, and here is it how it's done in the transformer winding. So you have all these parallel strands in one turn. Now, if you have this type of conductor, as you can see, all these strands are insulated from each other, but they are all part of the same turn of the transformer winding. If you get any insulation damage between the strands, like this, you get some insulation failure here. What happens is you lose some of the cross-sectional area, and the skin effect will be much greater in this one. So you will have increased eddy losses. This cannot be seen by the winding ratio or the turns ratio test. And it cannot be detected by the winding resistance either. Why? Because the winding resistance is done using a DC current. And the DC current actually uses the whole cross-sectional area, and the current is evenly distributed throughout the whole cross-sectional area. So for this particular test, you must use an AC current. So when you have this type of error, you will get currents circulating here, and you will have a higher loss. A higher loss gives higher temperature. A higher temperature you will see in the DGA, as explained in the first test. Now what you will do is you will make this short circuit impedance test at multiple frequencies for all three phases. So here you can see phase A, phase B, and phase C plotted from 1 Hertz up to 400 or 500 Hertz. Of course, it's the same type of winding, so they should behave very similar, and all three phases look the same. But if you have a short circuit between the parallel strand giving rise to the higher eddy current losses, a typical faulty curve would look like this. So then two phases look the same, and then one has an increased loss for the higher frequencies. And do you remember what the criteria was? Here, it should not be a bigger change in the resistance of 15%. So this is what you're looking for in the FRSL test. Frequency response of stray losses. When we talk about frequency response of stray losses, it is very often confused with the FRA test, the frequency response analysis test. That is a completely different test, which is the next test in the advanced test of the transformers. Do you remember from part 1 when we looked at the short circuit impedance? If we found that the short circuit impedance didn't give a clear response, they said maybe you should do an SFRA test, or sorry, an FRA test, because it is a little bit more clear in finding different faults. The short circuit impedance defines that the transformer behaves as it should be doing, or as it did in the factory, but the FRA test can find faults a little bit easier, and it will see that something is happening earlier. And the problems you will see with this one is shorted turns, core faults, deformation of the winding, displacement, or when the whole winding has moved or shifted place, core grounding issues, screen connections, or of course transport damage, but the transport damage will usually be one of the different faults listed above. The indication, pretty much anything defined compared to the TTR, which basically says when the book called relay trips, go do a TTR test. So this one will find the mechanical parts of the transformer that has been changed. In this technical brochure 445, they actually list two different methods. Method 1, which is the sweep frequency response analysis, which is called SFRA. And then you have the impulse frequency response analysis, the EIFRA. The difference is the sweep frequency has a voltage generator capable of generating a sinusoidal voltage at different frequencies. So what you do is you generate a signal at 10 Hertz, you measure at 10 Hertz, you stop generating, you switch to 12 Hertz, you generate, measure, stop, change frequency, generate, measure, stop, and you do all these different points of your test. While the impulse frequency response analysis is basically much quicker, because what you do is you send a quick pulse into the transformer, and then you record the response, and from that you do a FFT algorithm. So you do fast Fourier transform algorithm, and by that you can calculate the frequency response. The SFRA takes a little bit longer time compared to the impulse frequency response, but the accuracy of the lower frequency is much better for the SFRA, while the impulse frequency response gives actually very, very similar results at the higher frequencies. As it says also here, both methods give satisfactory results, but method 2 does not give results in the low frequency range. If you would like to know more, you can see technical brochures 342. And for this, when we look at the interpretation, the reference is your new measurement should be the same as your old measurement. So you need to have something to compare with. There are no limits defined. You need to have comparison with benchmark data. Very often, the SFRA measurement has been done when you have found a fault. And then you would like to say, is this okay or not? But if you don't have anything to compare with, it can sometimes be difficult. As a comment, it's a very common test to do as a transportation. Make sure that nothing has happened to the transformer during the transportation, but also no winding resistance should be done before the SFRA, as the winding resistance magnetizes the core of the transformer, and the magnetized core will influence the result. For this purpose, it is always good to do a demagnetization. For those of you who attended part 1 and listened to that one, you might remember what I said here. They say don't do winding resistance before any test. I say do winding resistance first and then demagnetize. Because after you have demagnetized, you know the state of your transformer and you know that you have no residual magnetization in the core. And all the following tests will be okay, such as the excitation current, the turns ratio test, the SFRA measurement. That can be very affected by a magnetized core. So the technical brochure says one thing, I say slightly different, but we both have the same aim to get as a good data as possible. So this is typical measurement result that you will get. What you see is actually 9 measurements. 1, 2, 3, 4, 5, 6, 7, 8, 9. Where you have taken the measurement on each phase, phase A, phase B, and phase C, or H1, H2, H3, red, yellow, blue, whatever you would like to call them. But I'd say you have 3 phases in your transformer. And what you do is you measure each phase individually. And you measure it first, you measure the high side, phase A, phase B, and phase C. You will find a result occur as a function of frequency. The standard says you should measure from 20 Hertz up to 2 megahertz. It is very clear on how you should measure this. You short circuit the low voltage side, so you actually do the short circuit impedance test again, and then you measure it phase A, phase B, and phase C. When you measure the excitation current, or the open test, as it's called, you have a very large inductance in your transformer. But when you do the short circuit, you actually remove the effect of the inductance. And at the lower frequencies, you see a very large change of the different curves. For the open tests here, you can see that you have 2 phases that are very similar. You see the blue and the green line here, they are almost lying on top of each other. And the mid phase, the red one, is different from the two other ones. That is a very, very good behavior, and it's typical excitation current behavior, which is the exact same thing that we're looking for in the excitation current test. So here you see two phases behave the same, which is the outer phases of the transformer, and the mid phase, for those of you who attended part 1, you know this, is deviating. When you do the short circuit test, you remove the effect of the inductance. Therefore, phases should be on top of each other. But when we increase the frequency, A, maybe, you have the winding, the turns, where you have a winding resistance. So you have a resistance in your winding, you have an inductance in your winding, but when you have a winding and a turn located to each other, you actually have a small capacitance between the turns. You have a capacitance between the turn and the grounded core. And you have all these different stray capacitance. And when I inject a signal at the top and I measure it at the bottom, my signal will attenuate. So my signal, how much it has attenuating frequencies. Now, if I get a short circuit between this turn and this turn, this capacitance, of course, will be 0. So then my complex circuit has changed, and I will see a difference in my measured curve. If I have a problem in my inductive circuit, you usually see it in the lower frequency. If I have some winding displacement or problems in my winding, you see that in the middle of the curve, in the mid-frequency range. And then you have the shorter, the small changes. Change that happens in this circuit will be seen in this measurement. So you will see almost any type of problem or any electromechanical faults in just one single test. But remember that you actually need to have a fingerprint, to something to compare with. The actual measurement circuit is a generator capable of generating a voltage typical of 20 volt peak to peak. The standard voltage now is 20 volt peak to peak. Here I usually mention, because it can be good to know, if I generate 20 volt here, my signal will go here, 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 or sorry, here, which means I have 50 ohm and 50 ohm, and I have my measurement point between the two 50 ohm resistors, or the 50 ohm impedance, which means my applied voltage here is actually only 10 volt, half the voltage. So if I say I generate 20 volt here, I will get 10 volt here. So sometimes we have seen that the data sheet of different instruments are a little bit misleading, where they actually say they have this generation capability, and some say we talk about the voltage at the transformer end. So just to be good to understand what you're comparing. So you compare the different traces with the correct foundation. So when you apply 10 volt here, you of course measure the applied voltage, so you have a reference. When we apply the voltage, it goes in through your transformer and it comes back through your circuit, and it has attenuated. So the measured voltage here, of course, is much lower. And then you measure that voltage, how big it is. And then you have the capability to look at this. Now we said, and I talked about this a little bit, we said that it is a comparative test, but just by doing one transformer, you can get some indication. When you do the high voltage with a short circuited, they should be identical with phases. When you do the high voltage open, you should have the two similar and one mid-phase change other response. And then the open and the close should start to align with each other, while the LV open should behave very similar to the high voltage open measurement. Now, if you measure something that looks like this, I can say already from this ones that something within this transformer is very problematic. So it's not useless doing an SFRA test, even though you do not have a fingerprint. Because here you don't have the typical behavior of an open test. Two should be similar, but here all three are different. All curves should align here. And here I see large deviation between all phases, and that is actually indicating some type of winding fault. So this is seen quite clearly from only one measurement. When you're doing the SFRA test, there are some things that is very, very, very important to consider, and something that can actually destroy your test. And it is the connection quality and the shield grounding practice. Then you have the instrument itself, and then how the core properties influence the frequency. This I have already mentioned. You remember how the DC resistance will magnetize the core, and the magnetized core has a residual magnetization, and then your SFRA measurement will be affected by that. So always do the test with demagnetized transformer. So this can also affect the response. The instrument dynamic range, it is how good this voltmeter is. If you have a voltmeter capable of measuring 1 nanovolt, you will be able to measure a much larger attenuation without any signal noise. But if your voltmeter is only capable of measuring millivolts, your capability of measuring a transformer will be affected here. So your noise floor will be set here. So you have millivolt, microvolt, nanovolt, which is basically how accurate your or how noisy your voltmeter is. That is very often specified for each particular brand of SFRA equipment. And as you hear, I say SFRA equipment. You have two different methods, the impulse and the sweep frequency. As of today, all the major manufacturers are using sweep frequency, and the impulse based is actually going further and further away. So when we look at the two top ones, connection quality and shield grounding practice, you can see it here. The connection quality means you should have a tight connection, you should have a good connection. It must be tight here, here, and especially here, because you should take a shield ground from the top of the transformer to the bottom ground here. And the connection quality matters very, very much for this one. With connection quality, you should have tight connection. Very typical, this part here at the bottom of the bushing is not connected properly, because you can have some paint on your flange of the bushing. So when you connect this, it's connected to the paint and not really connected to the metal of the transformer. So typically you can have a poor connection here. You need to make sure that you're connected through the paint and you have good contact, both here and here. Then I also said the shield ground practice. And in the Sigre technical brochure, they recommend method 1, where you have a straight shield ground. So this cable here is grounded, and then you have a connection point here or at the clamp where you can attach a ground braid, and it should be attached here, straight through or straight along the side of the bushing. Because if it's not straight along the side of the bushing, you cannot repeat the same measurement setup. Here you can see a typical example of something that is not recommended, or the second method, which gives you a frequency limitation of the highest frequency. Because if you have a cable that is connected properly at the top, and then you have a accessible point for the ground point here, and then you connect it correctly at the bottom of the flange of the bushing, you can see how this cable creates a worm. And you should be able to repeat the blue line. If you have the poor grounding, you can see how the higher frequency actually differentiates above 500 kilohertz. If you have no grounding, you have something here in between. So it is very difficult to repeat the same measurement circuit unless you have the proper shield ground practice. That's why they recommend method 1. And as you can see, this small difference in connection gives this difference in high frequency response. Now, if you look at the actual standard, it says you should measure to 2 megahertz. Now, the test equipment from Megger goes to 20 megahertz, which is completely useless. Above the 2 megahertz, you will only see the crap, how you have connected poorly or something like that. So you have no benefit at all in going to higher frequencies. That's a very, very quick going through of the SFRA measurement. With that, we go to the SFRA, or sorry, the FDS. Some also call this DFR, frequency domain spectroscopy, which is the FDS. DFR is the electric frequency response. This one is used to find water in cellulose, in oil paper insulation. You can see insulation failures, you can see contamination, and you can see acid. You get usually an indication from high moisture in the oil. So when you do a DGA and you get the moisture content in the oil, you say, oh, maybe I have also high moisture content in the paper, because those two actually is not the same. Moisture in oil and moisture in paper are not the same. Also, from the general assessment of the insulation condition, if you do a capacitance and dissipation factor or power factor test, you see you get a high power factor value, high tan delta value. Why do I have a high tan delta value? You can do a FDS test and you can get a general or much more better understanding of what's going on inside your transformer. You get the moisture determination by modeling. Comparison to fingerprint measurement, it's not really accurate, I would say. And then you can determine whether your transformer is wet, dry, or how it's done. The moisture determination is based on the transformer's measured response to a modeled response. This is all very well examined and described in IEC 600422 and also in a technical brochure. I don't really remember the name now, but I can send it out. Do you remember in the beginning, I said you can do the FDS, but you can also do the PDC and the RVM. The problems detected is the exact same thing. So there is no use in describing the different tests in another way, because I prefer to do the FDS, and I will come back to why at a later stage. The test method I will also show, but the principle of the measurement is exactly the same as the capacitance and dissipation power factor measurement, but you do it in different frequencies. It's quite a big theme in the advanced tests, because you have the FRSL, which is a short circuit impedance at different frequencies. Then you have the SFRA, which is a frequency response, which gives you a much wider base of knowledge. And then you have the tan delta test at different frequencies. I start by showing you a measurement example. So what you get is tan delta. Here you see tan delta. Tan delta at 50 Hertz, because this is frequency. 1 millihertz to 1000 Hertz, 1 kilohertz. The 50 Hertz is something that has been measured 100 years now. So this is a typical measurement that you have seen in. This is the basic test. You measure the capacitance and you get the dissipation factor, or the tan delta value. Now, as you can see, this frequency measurement actually gives a quite big change in tan delta. It goes from 0.3% to 150%. So it's quite a big range or big span. The measurement method is very simple. It is a voltage source which you apply over the high voltage winding and the low voltage winding. So the voltage applied here gives rise to a current through this capacitance. You measure the voltage and you measure the current, and from that you can actually get the capacitance and tan delta and the power factor as a function of frequency. Now, how is the polarization index or the PDC, polarization, depolarization currents done? In the exact same way, but instead of having a sinusoidal voltage source, you have a DC source where you apply a DC voltage, giving rise to a DC current, where you measure the DC voltage and the DC current. The only difference is whether you have a DC source or an AC source. Of course, this capacitance is the same thing. So what is the benefit of doing it over a wide frequency range? Because the insulation materials will change due to the different aging effects, both the capacitance as well as the power factor. And giving it a frequency response, you can separate whether it comes from the moisture, or if it's a temperature effect, or if it's a bad oil, etc. If I give you an example, you remember this curve that you measured? What does this mean? If I give you 3 different curves, you can see I get 1, 2, and 3. What is the difference between these 3 measured curves? Well, this red one, it is a very dry transformer. The moisture content in the paper is very low, but it has a very poor oil. The oil has absorbed some bad particles, giving rise to a high conductivity in the oil. So the oil gives a very, very high response here, but the paper in the lower frequency range and in the higher frequency range gives a very low response. If you instead look at the very wet transformer, which has very, very, very high moisture content in the paper, but it has a very good oil, you can see that in the higher frequency range, the power factor is high. Also in the lower frequency range, the power factor is, or the tan delta is very high. While for a normally service age transformer, the moisture content here. This is bad oil, this is good oil. How is that possible? Why is it like this? And in the table from technical brochure 445, they described that they had a model. How is this model constructed? This is how the model is constructed. Do you remember this is your winding? So this is typically your high voltage winding being constructed. So you can see how it's being going around this one. And then you can see that one here from the top. Can you see these boards here going straight along the surface here? Here's one, here's one, here's one. And then you have a big paper cylinder going around here. This is this one here. then you can have, depending on the size of the transformer, you can have 2 or 3 or 4 different paper cylinders and so on. Why is the transformer constructed like this? Because here you have an empty space, and when you fill the transformer with oil, this will of course be filled with oil. And on the inside you have the low voltage winding, and in the middle you have the core. So you basically have oil and paper between the high and the low voltage side. And if you look at this, you can see, if I take one here, cross-sectional area here, the red one here is oil, and then I have paper and paper. So I have a paper stick or a wooden stick, and I have a wooden cylinder going all the way around here, all the way around here. Now, we know that this is a wooden material, this is an oil material, and in the laboratory, you have measured the characteristics of the wood as a function of temperature. So you know how wood behaves when temperature changes. We have impregnated the wood with different moisture contents. So if you have 1% moisture content and 3% moisture content and so on, we have measured and we have seen how the wooden or the paper or the cellulose behaves with different predict how your transformer should look. So that is what you're seeing here. So we have taken the measurement, and you can see you have a model response, which is the green one. So you draw your own transformer with your particular moisture content, with your particular oil conductivity. And from that, you can say your transformer is very dry. It has only 1%. It's as good as new, on the verge of being very dry to moderately wet. So this is the classification from the technical brochures 342. Then you also have the conductivity of the oil, which means here, when the oil becomes worse, it becomes here. So this is what your model response looks like. When the moisture content increases, this one goes up, this one goes up. When the moisture content decreases, this one goes down, this one goes down. For the oil conductivity, this curve goes here. When it's bad, when it's good, it comes here. And then you can use this model described by the Sigrid technical brochure, and you can apply that on your measured response. And you don't need to have any previous knowledge of your transformer. The geometry here and here is, of course, how much paper you have, but the model is so intelligent that you don't need to know the geometry. You can just let the model find it yourself, and you will find the best fit, and from that actual response you will get the full moisture content. From one single measurement you will get the moisture content, you will get the 20 Hertz tan delta, the 25-degree oil conductivity in just one test. I said that you can choose to do the DC test or the AC test. why should I do the AC or why should I do the DC test? The DC voltage source, where you have the polarization and the depolarization current, the strength of that test is it's quicker. It comes, you need a shorter measurement time to get to the lower frequencies. Because what the polarization and the depolarization current is doing, it is actually taking the measurement and from a time domain, you take the current as a function of time, you use the mathematical model and you transfer it mathematically to a AC measurement. So you compare it in your same frequency model. So you change your time measurement to a frequency measurement by mathematical calculation, so you can use this model. So getting to these lower frequencies, it's quicker with a time domain measurement. You need less measurement time, but it has some weaknesses. Because this DC current that you're measuring is very, very low. So just a small interference current, it can be either AC or DC interference. You can see just a small nanoamp DC interference give rise to a very, very large error in your frequency conversion. This frequency conversion works very well, but if you have measured some kind of interference in your actual current, the conversion becomes very inaccurate. The problem with the polarization depolarization current is that you also need to discharge the measurement before you can start to do your measurement. And if you take the discharge into account when you're doing your full measurement, the actual measurement time is more or less very similar. And since you need to discharge, you cannot repeat your measurement directly after you have done a polarization color measurement. So you do your PDC measurement. When you're done, you need to discharge for the same amount of time as you took your measurement before you can repeat the measurement, or you will not get the same type of result. So there you have a big inaccuracy. So when we look at the AC measurement, where you have a sinusoidal voltage source, the strength is it's much easier to filter out any bad interference current. When you measure at 10 Hertz and you have a 50 Hertz interference current into your system, it is very easy to filter that bad current out of your measurement. And if you have an AC measurement, you don't need to worry about the DC interference at all, as it has no effect of the calculation of an AC current. And you don't need to do any data conversion, and the discharge or the repeatability is much, much better. The weakness is that it takes slightly longer time. At Megger, we have done a software that has a multi-frequency test signal, which means we inject 3 frequencies at the same time, and this reduces the measurement time to the same measurement time as a DC current measurement, but it has the accuracy of an AC method. So with that, I would prefer to do the DFR or the FDS measurement over the polarization depolarization current, as the inaccuracies of the different interference currents when you're in the field. If you're in the factory, I would say either method is actually quite well, as the interference currents are so small inside the factory. With that, I have actually finished all the different tests. I didn't speak specifically about the polarization, depolarization colors and the RVM, more than it has the same capabilities as the AC FDS. But as I said, the three tests are similar and it's the same problem that you're looking for. And here they use the same model for finding the result. So that was my last slide. I open up for questions, and I believe I didn't take too much of the time, as my aim was to get at 1 hour, and 1 hour.
That is a wonderful
Otherwise, I
presentation.
take those, and I thank you so much for all your attention and time.
Yeah, that was a wonderful presentation, Joachim, and thank you so much for your time in giving us here in Asia that presentation. Well, guys, for those of you who have questions, please write it or type it now in the chat box, and we'll read it for you. But as of this moment, I cannot see any questions here. So maybe we can give some few seconds. And while I'm giving them time, let me remind you guys that if you close this webinar, or for those who are leaving, there will be a pop-up survey, and please fill that out. And that will really, really help us in improving our future webinars. So I guess we have a question here from Nito. Okay. What is the recommended action if we find high moisture on transformer?
The recommended, it depends on when you measure. Here we can see two criteria. When you look at the standards, they say a new transformer should have less than 0.5% moisture content. But when we look at a service age transformer, when you come above 3%, we say it's wet and it's critical. But when we look at the different standards, some actually say that more than 2% is not accepted. And again, if we look at a generator step-up transformer, which take very, very high currents and the temperature is very high, I would say that those 2% is probably very, very, very relevant. But if we look at a smaller distribution type transformer, it's very bad to say a smaller distribution type. I should maybe say a smaller transmission type or a larger distribution type transformer, 20 MVA or something like that. If you go above 3%, it is not critical, but then it starts to be critical. I mean, sorry. My English is very, very poor at this stage. I have been on vacation, so I haven't spoken English for a very, very long time, so I struggle finding the words. I hope you can bear with me. But as I said,
No, you're good, Joachim.
When you're reaching the 3% for those type of transformer, I would say it's critical. I hope this answers that question. And again, there is no exact limit. I would say it depends on the size of the transformer and how critical it is.
Okay.
If it's a large distribution type, you might have a spare in some storage somewhere, which you can just bring in if something happens. But if it's a very special type of transformer with high MVA, which need custom order, which is very, very costly, and it takes 2 years to get a delivery time, then you might start to consider doing something already at 2%, because then you're running operating at a critical level.
Okay, thank you so much, Joachim. I have a personal follow-up questions on that. Will the purification of oil helps on that? For example, they get a high value of DFR.
If they clean the oil, they will also clean the paper. There is a very interesting slide on that. It depends on what type of oil purification technique you use.
All right.
And how long you apply the purification. Okay. If your purification operates at a very, very high flow of oil, you take 3,000 liters per hour at a very high temperature, then your moisture cleanliness of the paper will be much, much better compared to taking 200 liters per hour at a very low temperature. There is a chart describing this, saying that doing 40 degrees, 3,000 liters, cleaning a very large transformer paper takes about 1 year. If you use 200 liters and 20 degrees, it will take 30 years. So cleaning the oil will also help fixing the paper, but it takes time. It takes months. So you cannot clean the oil, which will be clean in a few days or in 1 day. So if you just go and do 1 day oil purification, no, it will not fix the paper.
All right. Thank you so much, Joachim. We have here another question. What are the recommended tests when transformer differential operates?
When the transformer differential
Differential relay. Yeah, differential
then
relay.
you have a typical grounding fault. So you can have some poor insulation. Or you have a turn-to-turn fault, because then you have a high current flowing between the turns. So it can be typically anything. I wouldn't say a winding resistance or turns ratio, SFRA test, and an insulation resistance I would do first.
And also, in addition to the relay, current differential or the transformer differential relay will operate also if you don't activate the harmonic restraint and the inrush restraint, then sometimes it will operate. So
Yeah.
Okay, another question. Should we do trending, and is there any guidance when to test again after particular high moisture finding?
The moisture ingress is very slow. You can do trending, but I would probably go out and I would check the transformer and I get the condition, and then I would do every 5 years. That would be my, if I would write the standards, I would do it every 5 years. It's no need for doing it every single year. Every standard check, I would do typically just one time delta measurement, maybe over a smaller frequency range, because you can get a quite good indication if something happens already with a smaller, a narrow band DFR. But for the full DFR, I would do it typically every 5 years, but there are no recommendations for this. Again, when you look at the technical brochure 445, they have different types of maintenance processes, if I can call it this. If you would do condition-based or if you would do time-based tests. So all of this is done more or less based on what type of process you have in your maintenance group.
Okay, Joachim, another question here, just maybe just last two questions because we already exceeded the time, but is any of these testing highly recommended for maintenance? Or maybe, yeah, as we discuss this advanced testing, do we have a highly recommended for maintenance testing?
Do you ask me as an instrument manufacturer? Of course.
All.
No, again, there is no standard. The technical brochure describes how you can test your transformer. It depends on your process. And for me, it also depends on the importance of your transformer. Again, a large distribution type transformer can be very, very critical if it supplies a critical industry. Then I would do full tests. I would do all the advanced ones and all of this one. But if you have a similar transformer only supplying some type of residential area, and you have a spare transformer sitting, or you have a redundant network giving you the possibility to reroute the current and the energy through some other way, maybe it's not important to do all these advanced tests on those type of transformers. If you have a generator step-up transformer, I would say it's very, very critical, and I would for sure do all the advanced tests. So again, what type of asset you have, what type of industry or whatever consumer you have, how important it is. So again, it depends on what type of network you would like to run or operate.
Yeah. All right. So we have a lot of questions actually, Joachim, but the time, is limited. So guys, in as much as we want to answer all those questions, the time is limiting us to do so. So yeah, we'll try to answer